Hello everyone, welcome to NCX Maths, and today in this video we're going to discuss on topology. So basically in this video we're going to discuss on what is a topology or what is a topological space, and then we're going to discuss on some examples of topology. So we're going to discuss on some examples which are topology, and also we'll discuss on some other examples which cannot be a topology for any given set. Okay, so let's start with the definition of topology, and it goes like this. Let X be a set, then a collection tau, so this Greek letter is known as tau, which is a collection of subsets of X, and if it satisfies the following properties, then we say that this collection tau of subset of X is a topology on X, and the properties to be satisfied are as follows. So we have first property is that phi and X both must belong to this collection tau. So this means this empty set and the X set itself must be a member of this collection tau. And next property is that a union of any subsets of tau is in tau. So this means if we take union of any subsets of tau, the union also must belong to the collection tau. And then the last property is that finite intersection of elements of tau is in tau. So if we take finite intersection of elements of tau, it must belong to tau. And the order pair X and tau together is called a topological space. So this means the set X with the topology tau together, it is called a topological space. So we can make this more clear with an example. So let's see some examples of topology. So here are some examples of topology. Suppose we have a set X equal to A, B, C, and then the collection of subsets, this tau1, phi, X, B, C, and then BC is a topology on X. So we can check this whether it is a topology or not. So we can start with the first condition, and first condition is that phi and X must be a member of this collection tau1, and it is already given that phi and X both belong to this set. And next condition is that a union of any elements of tau1 must belong to tau1. So for example, if we take union of this phi and X, we get X, and which is in tau1. And similarly, if we take union of X and B, we will get X, and it's also in tau1. And similarly, if we take union of these two, B and C, we get B, C, and this is also in tau1. So we see that union of any element of tau1 is also in tau1. So this second property is also satisfied. And similarly, the last one, so we take finite intersection of any two elements also belong to this collection tau1. So for example, if we take intersection of phi and X, we get phi, empty set, and which is here in the collection. And similarly, if we take intersection of X and B, we get obviously B, and it's also in this collection. Also, if we take intersection of these two, C and BC, we get C, and it's also in the same collection. So we can see that finite intersection of any elements of this collection tau1 is also in this collection. So we can say that the third condition is also satisfied. So this collection tau1 is a topology on X. Okay, let's go to another example. So tau2. So for the same set X equal to A, B, C, but the different collection tau2, phi, X, B, C is not a topology on X. So let's check this. So first condition is satisfied because both phi and x belongs to this collection. But the second condition, that is the union of any two elements of this collection. So if we take B and C, so union of this B and C is B comma C, but we don't have this element here in this collection. We don't have BC here. So we can say that this collection tau 2 is not a topology on X because the second property is not satisfied. A collection of all possible subsets of X, that is Px, or also we can say a powered set of X, is a topology on X. And this topology is called discrete topology. So collection of all possible subsets, that is the powered set, is always a topology on the given set, and it is known as discrete topology. And we can verify this very easily. And a collection phi comma x is also topology on X, and it is called trivial topology. So this means for any set, the empty set and the set itself, so this collection is also a topology on the given set, because we can verify all the properties that phi and x both belong to this set. So first property is satisfied, and their union, so union of phi and x is x, so which is in this collection, and their intersection of phi and x, which is phi, and it also belongs to the same collection. So we can say that this collection phi x is also a topology on X, and such topology is called trivial topology. Okay, so this was for today. So I hope you find this video useful, and if you still have some confusions, please comment down below. And as my request, please like this video, and if you are new to this channel, please subscribe our channel and turn on notification for more higher mathematics related videos. Thanks for watching. Have a nice time.